Hi, welcome to this video. Today we're going to go through the derivation of the ideal gas equations. I find this to be one of the trickiest parts in the A-level course. You wouldn't be expected to do the whole derivation in an exam, but you might be asked to do part of it, usually as to show that question. So I'm going to take you through the whole thing and explain it hopefully as clearly as possible. To start off with, we need to think about what is an ideal gas. An ideal gas is a gas that we assume has negligible particle size compared to the size of the container that the particles are in. The time between the collisions between the particles and the walls is much, much greater than the time for the collisions. The time before the collisions is considered negligible. We would say that the forces between the particles are non-existent, so there are no forces between the particles. Particles are moving randomly, and that the collisions between the particles and the walls are elastic. Okay, so starting out, we're going to consider our particles to be in a box. So there's our box, and we're going to say that our box is a cube in this case. So we've got dimensions of L, L and L because it's a cube. Inside our box is a particle, and our particle, we're just going to consider its velocity in one direction to begin with because it makes our lives easier. So we're going to say it's got a velocity of Vx. That's its velocity in the x direction. It would also have a velocity in the y and z direction, which we could call Vy and Vz, and we'll come to those later. So what we want to work out first of all is the pressure exerted by a particle, our particle, colliding with the side of the box. Now we know that the equation for pressure is equal to force divided by area. So we're going to have to work out what the force is and what the area is. We're going to start with the force, and we're going to use the fact that force is equal to rate of change of momentum. So delta mv over t. Now in this case, working out delta mv, we want to find out the momentum before and the momentum afterwards. So delta mv is equal to mvx minus mvx. And the reason it's minus is because you're finding the change, but also in one direction it is opposite to the other direction. So our change in momentum is therefore equal to 2 mvx. Okay, so if we substitute that back into our equation for force, we get force is equal to 2 mvx over t. So the next thing is, what is that value of t? Now we know that velocity is equal to distance divided by time. Now the distance that we're travelling in this case in between collisions with that wall is going to be there and back again, so it's going to be twice L. So Vx is equal to 2L over t, and therefore if we rearrange that, t is equal to 2L over Vx. So we can shove that back in the equation. So we've now got F is equal to 2 mvx over 2L over Vx. We can cancel out the 2's and rearrange that slightly, so we get mvx squared over L gives us our value of F. Okay, so we still need to substitute that back into the equation for pressure now. So pressure is equal to mvx squared over L divided by A. Now, the area of our surface, if we go back to our diagram, was L times L, so L squared. So we can go mvx squared over L divided by L squared. And that comes to mvx squared over big V for volume, because L cubed is equal to V. Okay, so that we've looked at has only got one molecule in. Most gases are not going to be just one molecule, so we need to consider what happens with more than one molecule, and we're going to give our number of molecules as capital N. Now, if we've got more than one molecule, we are going to have, each of those molecules is going to have a different velocity. So we need to take an average of those velocities. And the way we do that is by looking at the average of the velocities squared rather than the straight average of the velocities. And the reason for that is because otherwise the negatives and positives would cancel out. So that bar over the top, if you've not come across that before, is for the mean. So it's the mean of Vx squared. So if we're then putting those numbers in, we get that the pressure is equal to N Vx squared bar for the average divided by big V, or we can arrange that to be PV equals NM Vx squared bar. Okay, the next thing we need to consider is the fact that we've only been looking at one dimension so far, and the real world we need to think about three-dimensional space. So if we use Pythagoras' theorem, we can state that c squared bar, so we can say that c squared bar is equal to Vx squared bar plus Vy squared bar plus Vz squared bar. Okay, so that's simply just using Pythagoras. You'll know it as a squared plus b squared equals c squared. You can apply it to three dimensions as well as two. It works out quite nicely. Now, the next assumption that we make to make our lives a little easier is that there shouldn't be any difference between the velocities in the x, y or z direction, because why would there be? So we say that Vx squared bar is equal to Vy squared bar is equal to Vz squared bar. So that means that c squared bar is equal to Vx squared bar plus Vx squared bar plus Vx squared bar. So c squared bar is equal to Vx squared bar times 3. Okay, if we rearrange that to make Vx squared bar the subject, Vx squared bar is equal to 1/3 of c squared bar. Okay, we can then substitute that value of Vx squared bar into the equation we had up here. So PV equals 1/3 NM c squared bar. Okay, and that is one of our key equations. That's on your data sheet. That's what we would call the ideal gas equation. Now, the next thing that you need to be able to do is to take that equation and use it to work out the average kinetic energy of molecules in a gas. Now, to do that, the first step we go to is we're taking another equation alongside it, and that's our other equation for PV, which is PV equals nRT. Now, you'll notice here that we've got a little n, not a capital N. Remember, little n is for the number of moles. Important that we've got a little n in this one because we've used the molar gas constant. Molar gas constant goes with number of moles. You can alternatively do this with PV equals NKT, and the rearrangement goes in a slightly different way. We're going to just follow the PV equals nRT route. So we've got two things which have PV equals to, so let's equate those. So 1/3 NMC bar squared, or C squared bar, is equal to nRT. Now, the first thing I want to do now is to sort out what's going on with these n's, because we've got the capital N for the number of molecules and the little n for the number of moles. And what I'm going to do with that is I'm just going to bring the little n over. Okay, now big N over little n is the number of molecules divided by the number of moles, which means it's the number of molecules per mole. And there's a word for that, or an expression for that, which is the Avogadro constant. Okay, so that is a constant value, and we give that the letter N, or the symbol Na, subscript A for Avogadro's constant, and that's a number that you'll get on your data sheet. So we can then say 1/3 Na MC squared bar equals RT. Okay, so what we said we wanted was an equation for the kinetic energy of an average particle in the system. So we're going to use the equation Ke equals half mv squared. We want something equivalent to that at the end of this. So we can see there that there's an mc squared term already in what we've got. So I'm going to get rid of everything else from that side of the equation. So 3RT over NA. And then we need to half it. So half mc squared bar is equal to 3 over 2 RT over NA. If you had gone the other route and you'd done the PV equals NKT, you would have come to half mc bar squared equals 3 over 2 KT. Okay, and that is because K is equal to R over NA. Okay, now because everything apart from T on the right hand side of the equation is a constant, what this tells us is that the average kinetic energy of particles in an ideal gas is directly proportional to the temperature. Nice little result, mathematically proven, so easy. Not so easy, but I hope that that made sense. You will need to be able to replicate it. What I think is most likely that you'd be expected to replicate is that last section, the derivation for the kinetic energy. So if you can only get one bit down, get that bit. Okay, I hope this made sense. Do email me if you're having any problems.